I gotta say mix. All right, no, I messed that up. Okay, if I actually compare these little sample averages, the average of each of these, is it going to be the same as the entire population average? Each one of those guys? No, they'll be a little bit different, right? Okay. So these little averages of these guys, these are my X bars. The entire average is mu, okay? That's my entire population average. Oh, totally messed this up. I'm going to stop it. Vary throughout the population. We were like, how does, what's the probability of being less than this point? What's the probability of being less? So we were looking at just these individual guys and how they relate to the entire population, right? The entire population mean and standard deviation. Now, we're going to take a look at this. I'm going to take a sample of 5, another sample of 5 things. I better put 5 dots in there. Another sample of 5 things. And I'm going to look at how that sample or these samples relate to the entire population. So rather than comparing one data point to the entire population, we're going to compare the average of these data points to the entire population. Okay? So we're taking samples and comparing those to the population. Now, this makes a lot of sense in a lot of applications, okay? Because a lot of times, think about, okay, last night was basketball, right? Whether or not you liked the outcome, I don't know. I don't really follow any of that. Final Four. But guys, we could compare one individual person to the entire, all the players, or maybe we want to compare equal-sized teams to the entire group. And this makes sense, like to compare like team stats, right? To compare averages of the teams to the averages of the entire group. So rather than just taking an individual player's average, okay, maybe shooting average, why don't we take a team average and compare that to the entire group? Wouldn't this be done a lot, Wouldn't you want to know how an entire group is doing compared to the big group, right? Okay, so we are going to be looking at this situation and how does that change? What are we going to type in differently? Does it change how we're going to do our formula? So we've been doing this, and with this one we do NormCDF, right? Low, high, mean, standard deviation. This one, we're going to be comparing the low average of these samples, okay, to the entire average. So it's just going to look a little bit different, but it's going to be very, very similar. Okay, a sampling distribution of sample means. So we're doing a distribution of sample means. So we're taking little samples and looking at their averages. What was the letter that we used for sample mean? What Greek letter, or what symbol? Sample mean, sample average. Okay, X bar. We gotta have that memorized. X bar is sample mean, okay? So we're going to be looking at how a sample mean is distributed, obtained by using the means computed from random samples of a specific size. So they have to have a size. What letter do we use for the size of the sample? Maybe we know that one. Somebody, save me. A, B, C, D, E, F, G, H, I, J, K. And the sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation. So we'll talk a little bit about sampling error, but that's how far that is away from the actual population. Do you think the sample average is the same as the population average when you actually look at it? If I go back to this. All right. The mean of the sample means will be the same as the population means. So each sample mean is going to be different, but if we average all those sample means, it should actually be the population mean. So that's kind of interesting concept, okay? So if I average all those little sample averages, that actually ends up being my population average, okay? Now, this is as we get to really big populations, okay? So the mean of the sample means will be the same as the population mean. Now, here's the crazy part, though. The standard deviation, okay, the standard deviation will not be the same. The standard deviation is actually smaller, and it will be equal to the population standard deviation divided by the square root of the sample size. So on this next slide, you're going to actually, okay, ooh, that got messed up. As the sample size n increases, the shape of this increases without limit. The shape of the distribution, we take it without replacement. Okay, as previously shown, this will have a mean m and standard deviation. This slide got all messed up. Is it messed up on yours? Or do you have an actual formula there? The central limit theorem slide? Did it actually show a formula? Yeah. Okay. It just shows, okay. So what this is this part right here, this is all, these letters got all kind of messed up. This is supposed to be, I don't know why that is doing that. The standard deviation, okay, the standard deviation of, I gotta get my actual site. Can I see yours? Can I see what yours shows there? I'm sorry. Oh, that's supposed to be in where there. The heck. We'll have a mean m and a standard deviation. Okay, this is our new standard deviation. I think, here we go. This is a standard deviation of the sample means is equal to the standard deviation, the actual population standard deviation divided by n. Not a huge deal. You're going to see it when we apply it here in just a second. But basically, our new standard deviation, we're going to have to divide by the square root of n. Okay? It's a little bit smaller. This is a correction factor. We actually have to make a little correction for these samples. And so this is going to be our new standard deviation that we're going to be putting in. Okay? So standard deviation divided by square root of n. All right, here's the big thing. Here's our new formula. NormCDF. Okay, we're still using NormCDF. What goes in first? The low value, right? But I put low x bar. What is x bar again? I forgot. What's x bar? I just told you. Sample mean. So instead of the low data value, it's the low sample mean. Okay? So this is the low sample average, if that helps you. This would be the high sample average, because we're comparing averages now. The population mean still goes here, and then the very last thing you type in is the standard deviation divided by the square root of n. Instead of just standard deviation at the end, okay, you got to do that little correction that I was just talking about. You have to divide it by the square root of n. So this last little thing here is sigma divided by square root of n. This is population standard deviation divided by the square root of the sample size. That's because with these averages, the standard deviation of that is different from the actual population standard deviation. So we have to make this correction. So biggest thing on the last ones that you're going to be doing, your homework, you're going to see sample averages, and at the very end of your formula, you'll have to just divide by square root of n. It's not a huge deal, okay? But that's what the central limit theorem forces us to do. Awesome, let's do this example. So hours of television. A.C. Nielsen reported that children between ages 2 and 5 watch on average 25 hours of television a week. Right now, what is this telling us? This is our population average. That's mu. Mu is 25. That's not based on a sample, guys. That's based off of this huge report that the population average, kids watch 25 hours of TV a week. That scares me, ages 2 to 5. How much wasted time we sit doing that. Okay, assume the variable is normally distributed. Okay, so we can use a normal distribution, right? And the standard deviation is 3 hours. So this number here is our sigma. That's our standard deviation. Now, here's what's happening. Instead of comparing one kid, instead of saying, what's the probability that a certain kid watches more than 10 hours a week? Instead of saying that, I say, if we pick 20 kids between 2 and 5, so if I take a sample of 20, what's the chance that those 20 kids have an average of more than 26.3 hours? So I'm comparing a sample average to the entire population, not just one kid, okay? So this is a little different than our other ones in the fact that I have a sample size now. So this is n is 20, right? And I want to know what's the chance that it's going to be greater than 26.3. This is the average of this sample. So this is my x bar. Okay, that's my x bar. So my picture looks pretty much the same. I have my distribution. The average is 25. 26.3 would be above average. What's the chance that we're going to land way up here? Okay, greater than 26.3. So set it up. What do you think is going to go first? So we're going to do NormCDF. Okay, we always want to put in our low x value. Okay, and this time it's our low x bar value, low sample average. So the lowest we want to go is 26.3. Not this, this is the average, okay? So 26.3 goes in first. What do we put in next? E99, we're going to assume that they could watch infinite number of hours, okay? So E99 for our high. Comma. The mean goes next. What is the mean in this problem? The population mean. 25, good. Comma. Standard deviation, which is 3, but you have to divide that by square root of 20. So when you type it in, you're going to actually type it in just like that. 3 divided by square root 20. Okay? Don't get a decimal number here and round it and put it in. No, no, no. Actually type in that whole thing just like that. Okay, so a quick review of how we type it in. You go to your distributions, find NormCDF, which is the second one down. Your low value is 26.3. Your high value is E99. The mean is 25. That's the population mean. And then for standard deviation, it's 3 divided by square root of 20. Okay? You cannot just put 3. This is because we're comparing a sample mean, so we have to take into consideration that sample size. This is a correction factor, okay, for that sample standard deviation. So we got to divide by the square root of 20. Okay, so it looks just like that. Hit enter, and there's your probability of that happening. There's only a 2.6% chance. Thank God. So answer is 0.0263 or 2.63% chance that if we picked 20 kids that they'd have on average 26 or more hours. That'd be scary, okay? It already scares me that they say based on this report that they average 25. Okay, so this is central limit theorem, okay? I know it's kind of a weird name. Central limit theorem is done for comparing sample averages to the entire population average. Okay, so here's one more problem for you here. Vehicle age. The average vehicle registered is 8 years or 96 months. Assume a standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that it's between 90 and 100. Okay, so if we take a sample of 36, what's the chance that the average age is going to be between those 2 months? Okay, why are they doing it in months instead of years? Because years are pretty vague, so months are a little more accurate, right? So just say here, since a sample is 30 or larger, the normality assumption is not necessary. When you have a sample that's bigger than 30, you don't even have to assume normality. You can just use normal distribution. So anyway, we're going to assume that it's normal is what this is saying. Okay, so set this up. Think about what you're going to put for your low, for your high. Pull it apart. Should we use 8 for our average or 96? 96 because everything else is in months. So that's mu. This number here is sigma. This number here is n. That's what we have to divide by the square root of that, right? This is my low x bar, and this is my high x bar, okay? My low and my high are given in the problem. Did anyone just type in 16 divided by 6? Do the square root of 36 mentally? Square root of 36 is 6, right? Okay, we need an answer for this. %? Okay, 0.9209. Does that sound right? 90 and 100? Yes, no? How are we doing? $96, 16 divided by square root of 36, yeah. Okay, 0.9209, we'll round that to 1. Okay, so 92.1% chance that this is going to happen. Okay, here's one more for you to work out. I'm going to kind of be quiet and let you guys work on this. If you don't have the PowerPoint brought up, I'll kind of slide this over here so you can see it. Hopefully it's big enough. And then I'm going to call on someone to find out how you have it set up, and then call on someone else for the answer.
Could you move it down? See ourselves in the top right. Great, thank you.
This is a probability, so we shouldn't have negative numbers. The question was, can we get negatives? Not with area or probability. So it looks like mu is 7.93. Standard deviation is 0.8. Find the probability an individual who works that trade works fewer than 8 hours on the weekend. An individual, what does that mean? Sample size of 1. Wait a minute, so then we would divide by the square root of 1? Isn't that just back to what we were doing before? Dividing by 1 does what? Absolutely nothing, right? So in other words, if we have an individual, this is the same as, okay, just an x value. It's not going to change the answer. Now, if you want to divide by the square root of n, you can, because this is in this section, but it's not going to change the answer. So fewer than 8 means 8 or less, so we're going from negative infinity, right? All the way to 8. And you don't go to 7 because we can go to 8 because it could be 7.99, 7.999. So we go ahead and put 8. And then your mean and your standard deviation. Okay, and your standard deviation is 0.8 here. Okay, make sure you type that in correctly. Okay, let's go with Allie. You got an answer?
Oh, the answer?
Yeah.
0.5349.
0.54, what'd you say? 0.5349. Okay, there we go. Okay, so about 53%, 53.5%, right? And as I look at that picture, Does that kind of make sense? Should be a little more than 50%, right? 50% would be right here at the mean. It's a more than 50%. Good. Because this is above average. All right. We are not covering the finite population correction factor. So we're done. That's a